Okay, so welcome everybody. Thank you for coming to our Lunch and Learn. Today, Mike Sawada is going to present on deep mapping. Mike is a full-time professor at the department. Okay, Mike, take it away.
Thank you. So I'll just share my screen here. There we go. So deep mapping is what I want to talk about today. Here's one example of deep mapping, which is how the Great Barrier Reef was mapped using hemispherical cameras. This is how Google did it. This is a Google setup here with a 360 degree hemispherical camera, and they're mapping, the coral reefs, and you can go on Street View and see those things. That has nothing to do with what I'm going to talk about today. That's a different type of deep mapping, obviously, than what I'm going to talk about. So I'm going to be talking about the application of deep learning to geography and into mapping and automated mapping of the environment. And you've certainly heard about deep learning in the past few years, as it's often in the news. AI, so it's a subset of artificial intelligence and machine learning. And you've seen that now we have AIs that can beat anybody at chess, beat anybody at AlphaGo, and things like that. So these type of things are developed through what's called reinforcement learning. There's all kinds of different approaches in the deep learning tool set, for example. Also automated Amazon Go. So stores where you walk in, you just put whatever you want in the basket and you just leave. And everything is recorded by cameras set up. And computer vision is used with artificial intelligence and deep learning it to figure out what you bought, how much it's worth, and charge your credit card automatically. One thing that's good about deep learning and applying what we call deep learning to mapping is an example like this, where AI achieves better results in finding moon craters than humans. And this is one good thing about deep learning and artificial intelligence, is that yes, you can train something to do better, to do visual counting exercises or visual identification exercises better than humans do. That's all it's good at. It's not smart or anything. It's only good at one thing, each type of model, so to speak. Then, of course, there's the naysayers and the ethicists who impede progress in deep learning, or not purposely, but it tends to, and sometimes I think impede some progress, where one-off things like a self-driving Uber car or a Tesla car kills somebody, which is horrible, and often not always the fault of the AI system, for example, but it gets the media picks that up and demonizes it, and there's you've heard the Tesla CEO talk about fear of computers taking over the world. And of course, even Stephen Hawking thought that within 100 years, we'll be, potentially slaves to AIs, basically. So there's all kinds of benefits, but there are also issues and ethics that have to be looked at in these things, because there can be biases within any machine learning model. Now, machine learning, just as a quick history with neural networks, in the 80s, neural networks were big because they were fairly new. And these were what we call feed-forward neural networks. They didn't perform that great. And then we had more complex networks like LayNet by Thomas LeCun. And this was the first type of application that we call deep learning. But when it was done back in the 90s, you still needed like supercomputers. So these big giant supercomputers or clusters to effectively do that with large data sets. So it fell out of favor, and in the 2000s, things like regression-based analyses, support vector machine analyses, decision trees, boosting, and stuff like that became very popular. Even today, these are still very good machine learning techniques. Obviously, depends on the question you're looking at. But what happened was people weren't using neural networks anymore because they didn't perform as well as these other techniques until 2012, when NVIDIA, a popular gaming video card maker, produced cards which were good at massive parallel processing. So video cards that could parallel process a lot of things quickly. And then from then, deep learning became a possibility that you can now do on your desktop. And so it's exploded since then in usage and application. So that we call that the age of the GPU, or graphics processing unit, for deep learning applications, particularly in computer vision. This is fundamental. Now, for those of you, just a quick idea of what a neural network is. So basically, everybody's familiar with the data sets that look like this. Here we have data set saying car ownership, and we then have records with individual income, debt, age, and all kinds of, there could be other variables obviously in here. These are just some examples, like income, for example. And can we predict car ownership, which is an indicator here, 0 or 1, for each of these things. So you have, for this person, they make $35,000 a year. They don't own a car. This person makes $55,000, they own a car. Person $123,000 owns a car. So, there's relationships in there about car ownership and income, for example. And we feed that into a neural network. Let's say we just have these 3 inputs, and we feed them into what's called the input neurons, or input layer. Each item in the table, each value has an input: income, debt, age, for example. Then we have what's called hidden layers. These hidden layers are called perceptrons. They mimic neurons in the brain in some way. That's what they're meant to be doing, right? So we connect each of the inputs to each of these hidden neurons. And there can be multiple ones. The number in the middle here is variable. There's an optimal number that you can find through optimization. But here we just have 4, for example. And then we connect everything to everything. So every input is connected to every neuron in the middle here. And every neuron in the middle is connected to these 2 outputs, which will be either yes or no, like so. Then we have weights. Weights are assigned randomly between 0 and, they sum up to 1. So they're assigned randomly to each of the connections from the inputs to the hidden layers. So these are just numbers. And then in the hidden layers, there's a simple linear regression equation. So each perceptron basically is a linear equation. Each neuron has a linear function like this. And that then the output, f at x here, becomes the weights that are connected to the outputs right here. And what this is trying to do ultimately is to figure out how to map, or what the optimal weights will be, in order to map the inputs here to the correct outputs, yes or no. And so what happens is these weights then are summed up in a way to give values like that: 0.7, a probability, and a 0.4. So there's probabilities of the output, 0.7 or 0.4. And then we have a function that computes the difference between the values from the table that were the true values right here for each input. And that is then used, that information there, the differences are used to update the weights. So those weights are all updated. And then the output layer probability is updated as well. And that keeps happening until you get a good prediction. And so neural networks, and this is called just a regular neural network. This is the 1980s neural network. By adding more layers in the middle, once you have more layers than that, like 2 layers, that's called deep learning now. So deep learning is when you have more than 2 layers in the middle that translate the input values to the predictions on the output. What's happening in here is not a complete mystery, but it's largely a mystery. It's a kind of a black box approach, in that these neural networks are great at prediction, but they're not going to tell you which variables that you input are, let's say, explaining the most variance in the output. What this is about is prediction. Where prediction is important, these will perform best if they're properly created. Now, with computer imagery, of course, or imagery, satellite imagery, street view imagery, we have pictures. So we don't have a table of numbers, but we have pixels in the picture. And we have multi-bands or single bands. I'm just showing here, this could be a satellite photo. This happens to be a street photo. It doesn't matter. And then we have what are called receptive fields or filters. So just these are called convolutional blocks. This is a 3x3 neighborhood filter inside the goes over the image step by step, and that connects to a neuron in the hidden layers. So each receptive field has a neuron in its hidden layers. Then you hear the attachment here is just showing one as an example there. And of course, that is the same thing, the linear equation that we use in each of these. And there can be hundreds of those hidden layers when you're working with imagery like that. So what do those layers look like? Well, what happens is that from an image like this and many images like this, that filter goes across, and that filter is learned, and it provides, for example, here, non-horizontal edge detection. So this is something that is this filter is learned by that process of, randomly starting with numbers in the filter that map to the output, and then updating those weights to better predict the output every time. And so filters are learned like this one. This is a first level filter in the first convolutional block of a deep neural network. And it looks like that, for example. And also some more filters that are neat later on. So how do we apply this? Firstly, one way we applied this was to gentrification. So Lazar, Illich, and myself and Amore Zarzelli, we created what's called GentriNet, which is a gentrification CNN. We published this in +1, and it got national and international attention. Here's some of the just a few of them. There's many more where this work was either we interviewed for it or was put into the press. Why? Because it was the first time it was ever done in this context. And that's kind of a lesson. If you can do something the first time, try to do it quickly as possible, but of course with quality to get that output. So there's deep mapping gentrification that we apply. How do we do it? Well, we start by getting training data. So that's the data set that goes in to the neural network, so the neural network can learn how to identify different things. And we present people with these two. So we use people to get the training data set. And we show them two pictures, right and left, and we ask, for these two different pictures from two different time periods, does the left one or the right one show positive change in the aesthetics of that structure or property? In this case, the person would choose no. Then they see another web interface with two other pictures. Here they would say yes, and here's another one where they would say yes. Here's another one, another example from our training data, where the person might say yes, because you can see that there's a new house being put up here, for example. These are just examples of new build gentrification that we use in training the data, training the CNN, the convolutional neural network. And the training data ultimately looks like this. We have a latitude, a longitude for mapping, and then we have a date, start, date, end, and yes or no, whether there was a gentrification-like change, basically a property improvement. Now, we feed this through a 19-layer, which had 19 layers. So this kind of looks intimidating. It's called a Siamese CNN, a very underused type of architecture in the context of deep learning. It's becoming more popular now. And what we do is we have an input image on this is like a left image and a right image, and we know whether or not there's been an improvement because the people have told us when they clicked on that image. Like here you can see there's been a change in the property from a dilapidated old boarded up barbershop to a newer condo. And so by going through all of these layers, and each of these again has just as filters, like I showed you, that edge detection filter. Each of these has filters that are learned, where the first convolutional block is just the image, basically, the input pixels. The second one will have like those edge detection filters. And then from those edge detection filters, these further smaller blocks abstract the information. So they learn abstract concepts about the spatial configuration and geometry to find the output, just a simple thing at the end, which is yes or no. Did I see a change or do I not see a gentrification-like change? What is the advantage of this? Well, we can produce or run the model once it's trained on millions of images within an hour. And there's no way a human could even do that. So some example of predictions that we see, here's 2007, that's at Barbershop again. And this is actually from the model output. 2007, 2009, no change. And then we go to 2009, 2012, no change. And you'll notice here that the pictures are in different exposures, different slight angles and stuff like that. And one of the advantages of deep learning is that it knows to ignore those things. It learns that those aren't important when I'm looking for this particular thing called gentrification type changes. And then we go through 2014, for example, and we see a change there, and that's registered as a positive change by the model. And of course, you can have some cases like this one, a double change because it sees an improvement from this to that, which is obviously clear. That's a much more aesthetic improvement. And why aesthetics? Because aesthetics of a property are the outward expression of wealth for many, and social status for many people when they either purchase an old home or demolish an old home and put up a new one. Now, none of these are gentrification. So this is not necessarily gentrification. Gentrification only happens if there's a critical number of these things, of changes like this, within a particular region of space. So this is, again, just showing another example. I'm going to go through that, forward through that, but just showing you again that, even obscured by trees, different vegetation, it knows enough to say there's been no positive change. Again, then from there to here, no change, but yes, from here to there, a big change, So it's quite good. Now, what we do then is we map out where those changes are. And this is the idea of deep mapping, the application of the deep learning model to spatial data. And once we map it out, we can see where the hotspots are, where we're having a lot of these changes happening. In some areas are well known for gentrification, like the Westboro area, Island Park region, Hintonburg, Mechanicsville. So some areas, it confirms that what we already know, but then it finds areas that we didn't even know about, like in Crestview, Meadowlands, and some other regions which are undergoing gentrification-like changes. And that's because there's multiple locations in space where the changes are taking place. And when you have enough of those, we call it gentrification. How many is enough? Nobody knows. Nobody can say, well, is 10, 20, or 30. And we can also then break that down through time, because we use Google Street View imagery in this case, and it has a timeline. So we downloaded the timeline for each location and then had the model go through that. And that's what we were seeing, and able to produce then time slices of the process, So 2009, not much happening. But between 2009 and 2012, we start to get a lot of these things going on. There's another example of a property improvement that would be picked. These are just model examples. These are examples that were predicted from the model. And there's another one there, another type. And these are some of the filters in the later on in the convolutional blocks. So in those deep convolutional blocks, you start to see really nice patterns of neuron activity. We can't explain what these are, of course. These are just things that are helping that model to predict whether or not there's been a gentrification-like change. And some of them are really neat like that. More recently, we created CrutiNet, and this is a walkability convolutional neural network with myself and Arnaud Grégoire. We did this a couple years or so ago. In this case, we also take the Siamese approach, but we add another type of what's called a ranking neural network as well on there, so that we can learn from images what makes something walkable by people saying, I'd rather walk here or there. And then having learned that and having weights for all of these convolutional layers, all the filters are there now learned, we can then use that to rank individual images and produce maps like this of perceived walkability. And this is fundamental because you can't get at this construct about geographic space any other way than either you do it through checklists and having hundreds or thousands of people go and do checklists for every street, or you simply train a neural network to get at the basic construct of this is more walkable than somewhere else. And it makes sense that, highways and stuff would be less walkable, the red. The blue is the most walkable ones here. And these are just the raw scores. It's an unbounded output. So it's relative. High values, more walkable, low values, less walkable. And we also applied that same model to Paris to see if it would make sense there, because we trained it on North American data. And it actually made sense, pretty good sense in the context of Paris as well. Other things we look at in there are trying to find ways to engineer additional data when training the network. And one of the ways we used was creating what are called generative adversarial models, or a particular type of network that trains itself basically to create this. This is a creation of the neural network based on input street view imagery like this. And we have the computer create average scenes like this of walkability and whatnot, just to help out. And I'll just wrap this up. And these are just some scenes, low resolution because of we had computational limits, but just some scenes, again, constructed completely by a neural network to help us with our training of another neural network. And TechieNet is another one for assessing green space. So again, we do the same thing. People compare images of green space. Where would you rather walk? Where would you rather spend time? We use a meta model and a ranking model architecture in this one as well. And then we can rank green space. And we did this using now what is called mapillary, which is a citizen science street view clone. It's not open source, but it's free to use, whereas Street View is no longer free. It's exorbitantly expensive to use for this type of application. And one of the challenges with user and not using Street View is that we had to do a lot of work in OpenCV, which is a Python library for working with for computer vision. We had to do a lot of work in actually the quality of imagery that was available. And then we can eventually map out green space like this, where each dot, the green means higher, more quality green space, and the red means lower quality green space. And this is, of course, to look at in the context of the Ottawa Neighbourhood Study that I co-lead, to look at inequalities in quality of green space across Ottawa, which is fundamentally important. Thank you very much.
Thank you.
Sorry, I went 2 minutes over there, but
no, that's awesome. Thank you so much. That was awesome.
You're welcome. Thanks.
Does anybody have any questions for Mike? That was a really good presentation.
Oh, Mark Sainer, I think, may have a question, but he must unmute himself.
I don't have to go first. I always have questions, but I don't want to go first necessarily. So
okay,
I can go first, Mark.
Go.
So Mike, we've heard a lot of stories about the use of this kind of AI and how it's biased to its training data. Worst, when it becomes used by police forces and so on. So the volunteers that you got to help you tell whether some change was a gentrification or whether a neighborhood was walkable. Did you do anything in terms of selection of the people who helped you train it, or how does that work?
No, and so we were trying to get at a general construct. So we didn't care who, what person did it or what they were thinking about when they chose a left or right image. But that also means we didn't control it for, we didn't select, let's say, different groups of like disadvantaged people, for example, would be one group. Another group could be old people. I mean, people over 65, that type of old people. Another group could be, a BIPOC community or LGBTQ plus community, which would see different things about, let's say, walkability, for example, right? What might be walkable to one person may not be to another. And generally, when we don't look at that, then there is biases absolutely in the output. How the degree of biases, we don't know. So what we've done, and just before the pandemic happened last year, actually the week before the university, the week after the university closed, we were still able to get in. And what we started to do was to look at these biases by starting with old people. So we had a bunch of old people come in to a lab, not one of our computer labs, but to a lab over in social sciences, which is more conducive to these things. And they sat down and they went through and did thousands of training examples so that we can then start to compare what the general type of model looks like and what it's choosing as a very walkable region versus walkable, or we're looking at a bunch of constructs that we're trying to figure out the biases of. So they look at it, we train a model up, and we see how does that model compare then to the more general one where we didn't control for different groups of people, to see what degree of biases actually exist, starting with these with that group. And we had planned to do that with other groups as well. Unfortunately, the pandemic hit and research stopped on that, and then we're picking it up this summer. So yeah, there's biases because the training data that goes in is often very biased, especially when you're looking at things like facial recognition and stuff like that. A lot of this AI, especially in Facebook and Google, are used for mining of micro expressions. So because of the population distribution, let's say in the United States, Canada being mostly, predominantly white, for example, the mining of certain facial expressions and stuff may not work as well on marginalized or, minority groups, for example, like that. To mine, let's say, to figure out what is this person likely depressed? So should we show them an ad about, Pfizer's new antidepressant versus, something else? And so, yeah, biases are a big issue in AI right now, and the ethics around that are around these things are just being developed at the same time. And in some cases, yeah, I was joking when I said ethics impede progress, obviously, but maybe I should make sure that I'm joking when I said that.
Thanks, Mike. That was an excellent answer.
Okay.
Yeah, thanks for the ethics clarification.
Yeah, I'm sorry. I make jokes sometimes, and they're funny to me because I know I'm joking, but nobody else does ever. And I have to remember to tell people that I'm making a joke when I say things like ethics impede progress, which is actually some people's opinion. It's not mine, but
well, I mean, there's some foundation for that. Yeah. No, I did get it, but no, just let me just ask actually a couple of ethics questions. So the bias is one, and I know people who have openly written in the literature that the algorithms, Facebook, etc., the AI is racist. That was just summary. Racist.
Absolutely.
But there are more issues, and two very popular big issues in AI ethics. One is technological unemployment, displacement of jobs through these very competent systems, and the second is so-called dual use, which is true for all technology, using a hammer as a weapon, or using for example, your gentrification algorithm to plan the invasion of Ottawa with using tanks or something, I don't know. So I'm just curious, do you feel as a researcher that you should pay attention to who is using your info, how they're using it, and if it affects, let's say, these major categories such as fostering bias, fostering inequality, unemployment, and ultimately dual use?
Absolutely, and I like in our paper we talk about the limitations. Obviously, like any scientist talks about limitations to what they've provided in the paper. Now, the problem is the media, the real estate companies, and the lawyers don't read papers. They read what's in it, in an article or something. So people don't realize or understand the potential biases or limitations of what's being done. They just want to apply it. I had a in Ottawa, for example, a couple. There's litigation going on over the Timber Creek evictions, which is forced gentrification of in one of the neighborhoods in Ottawa, where they tore down a bunch of low-income housing, which was 90% BIPOC population, by the way. And so the city forced the eviction by Timber Creek, the developer, because they wanted to redevelop that area with condos. So there's litigation going on, and the lawyers contacted me about using this research in there. And, I explained to them, absolutely not, because there's limitations to this that can't, would be not, well, basically, this is not the intention. We're only looking at outside. So, for example, like in gentrification, for example, we only looked at outside or exterior indicators of gentrification.
Okay,
right?
But
you need to go beyond that, and so you don't use this type of research as the only means to find out where gentrification is happening. It's another tool. Yeah.
Just to simplify, when I write stuff, I almost never pay attention to what happens later. It's like, once the child is born, it's in the environment, good luck. Do you spend the effort, because of the power that this could represent, do you spend the effort to follow who reads your papers and who cites your paper and try to figure out who they are? Do you actually do that for your, or do you just publish and then go to the next project and publish the next paper, like most people?
I would say 95% of the time, I just publish the paper and whatever, I look at the citations. I don't care who cites it. I just want it to be cited in good journals. That's a major indicator of success in academia, is the number of citations you get to your articles. This one, however, I've looked at more detail, and so has Lazar, for example, to see who's using it and in what context, because it got a lot of media attention. A lot of people know about it and are, using it or looking at it and citing it. And that's good from that perspective. And so far, it's not been used in any like nefarious way or unfair way or anything. It's often just cited in a sentence in somebody else's paper that's doing something similar now. But yeah, I think it would be difficult to fully, follow the implications of your papers, depending on what they are. And I think, it depends a lot. Like if you're doing a paper, let's say like on a river and the discharge, and then somebody uses that that information, let's say about, to sue the city or something with flooding, you never know about that stuff usually. But it's a good point, and certainly guilty of it.
Yeah, no, that's not my implication. I'm impressed you're even doing that. So good for you. Thanks a lot. It was really interesting.
You're welcome.
Sydney, go ahead.
Great presentation, Mike. It was very interesting. A lot of it was a little too complicated for me, but
sorry about that.
No, it was great. I was kind of wondering as you were talking, because I live in Hintonburg, which is one of the areas you mentioned is being gentrified pretty quickly. You wouldn't believe what we pay for rent on like this teeny tiny apartment in this neighborhood, and there's buildings going up all over the place. They're tearing down so many old condos, buildings to build condos. I'm just wondering, with the building of the LRT and now it's expanding a bit more, that must be affecting which neighborhoods are getting gentrified and walkability. Is that something that you guys are finding in your study at all?
We don't have that spatial, we don't have that temporal resolution yet.
Okay.
Unfortunately, so we can't look at it, but I think you're dead on with what your observations and what's probably going to be happening. Yes, property prices near the LRT are going up, because of the city's smart growth. But Hintonburg and Mechanicsville was not forced, but planned gentrification by the city, because 15 years ago there were houses the row houses they used to have in Mechanicsville and Hintonburg before they tore most of them down, that were being sold basically for demolition. So it was just the property values that people were buying. And now, of course, with gentrification, what happens is exactly what you're experiencing, is that you end up being priced out of the neighborhood and the culture that you lived in. So you can no longer probably soon, maybe in a couple of years, you may not be able to afford rent there anymore because it's gone up so high, because all the the gentry, so to speak, or I say more affluent people who want to associate themselves with a particular lifestyle, move into regions, of course, change the culture completely. And Toronto, I think, has a lot of places like that as well. So
yeah, I was just thinking about that. It's very interesting because I have noticed that in my neighborhood, they're just about to build this. They're in the middle of building this huge tall building, and they're going to charge $2,000 a month for a 450 square foot apartment. And I'm just it's just pretty shocking. And I think the train might have something to do with it, because it is very convenient to be so close to this. Like, walkability aspect is for sure a huge part of that. Like,
yeah,
the accessibility.
absolutely. You know, and qualitative walkability is not something that's measured by, you can't measure these things with quantitative data. So with regular GIS data, layers or whatever, you can't measure these things, because these are things that exist in people's heads as concepts or preferences. You can try to measure them through interviews, but not at the spatial resolution that we're trying to do. And that's kind of the advantage of what we're doing. We can now do this at, you know, the finest spatial resolution possible across large regions. But yeah, in terms of, then we have COVID-19 gentrification that's been happening as well. You know, for example, now if I was to sell my house right now where I live, even though I'm well compensated as a professor, I'm not complaining, I wouldn't be able to afford to buy in my own neighborhood anymore. You know, houses in my neighborhood are, one around the corner went for 1.2 million, and I'm not in a super rich neighborhood or anything. I'm just out in Orleans, you know.
Mm-hmm.
And yeah, so that's going to be an influencing factor as well, I think, in people's choices, and as more people want to move out of, I guess, smaller domiciles and whatnot.
Mm-hmm. Thank you.
You're welcome. Yeah.
Sarah, you had a question?
Yeah, I was just going to say, related to sort of this qualitative measure of walkability, it's something I've been thinking a lot about in the past week, because personally I've been having like a lot of anxiety related to the case in the UK where a woman was kidnapped and killed, and you know, you hear these stories and it happens everywhere. And so I'm interested how, you know, there is this female perspective about what's walkable for a woman is very different from what's walkable for a man. And so I'm sort of interested in how that plays into the AI, and whether the people informing the AI are, multiple, identify along that spectrum of gender, I guess.
Mm-hmm. Yeah, certainly that is a fundamental question, and that hasn't been explored much in terms of the AI applications of it. And yeah, we as we were starting last year working with seniors, you know, we were asking more questions of like, where would you feel safer, which way, right? Now we had a gender balanced group there, but we have not yet done any group with, let's say, just women in walkability, and that's something I want to do. And that needs to be done to address these issues of biases in the literature, and to see how people view, you know, the environment as they belong to different groups. You know, and yeah, I can understand the anxiety, you know, that you must feel. It must be a horrible feeling, you know, to think that you know you can't walk down the streets where you live safely. You know, I can't imagine that. You know, as a male, for example, I can understand, but I've never felt that. You know, so, but I'm certainly sympathetic.
Yeah, I was talking to my friend last night, and I think it's something we also don't talk to men about, just the number of times, because when we walk down the street with men, we don't have that same level of anxiety. So it maybe is one of those things where it's like, oh, did you see how that car just pulled up to the side of the road? If I was on my own, I would feel uncomfortable because someone could get out of that car, and, you know, and it's like you walk past a doorway and, oh my God, there was someone standing there smoking. It's like, you know, all of these constant things that, because we don't always talk to men about it, you know, it's not something that maybe has been, we can't blame men for not knowing what they don't know. So maybe that's part of the conversation going forward.
I think so, yeah. And I think, you know, for men to realize as well, you know, that there are these differences, you know, in the perception of the urban environment is, you know, the first place to start. And then we can examine those and research them, because it's fundamentally important to do so. It's amazing, yeah. And that would be something we had planned on doing as we got into those things last year. And then everything, I haven't done any research in the past year. All I do is prepare courses. So unfortunately, but yeah, hopefully when things get back to normal, we'll be able to then pick those focus groups back up, and, you know, work with a number of different groups to see what these biases are, because that's something that is not in the literature at all. Other than the conjectures, right? Other than the conjectures.
For sure. I'm sure that's also changed with now people have to be 6 feet apart. So it's like, now how do you walk, and that kind of thing.
Yeah, that's a real wrench in the plans for sure. Thanks, Sarah.
That's awesome. Thanks, guys. Any more questions for Mike? Okay, well, it is, oh, Tony says, great talk, Mike. Thanks for educating me. I was going to say magical, but that may sound like a comment on the methodology.
Mm-hmm. Yeah, well, I think, have a look at that lunar paper and think of Banks Island.
Yeah.
Catherine and I happened to be talking about you, Tony, before we started this. So it's just kind of, I'm glad you were here. We're talking about your paper on Banks Island. So.
And all those thaw slumps. Yeah.
Yeah. Oh, yeah. Oh, well, thank you everybody for coming.
Yeah, thank you all. And I don't think we have a lunch and learn next week, but we'll have one the week after that on the 30th. And Sonia is going to be presenting on the 30th, and that's a Tuesday, FYI. Okay, thank you all for coming. Have a great day and have a great week. Bye, guys.
All right, thanks, Mike.
Thanks, Mike. Bye, everyone.
Thank you all. See you.